Now that we have a reasonable understanding of how we are going to do the numerical integration problem, let's get a bit formal. Now, on top, you see the expression for the interpolating polynomial based on forward differences, and the order of the interpolating polynomial is m minus 1. Polynomial came out in powers of alpha. We are able to reach any x value by changing the alpha value. This is something you know. You also know that h is the step size. And when you have the polynomial of order m minus 1, that means you're having m parameters in that model, in that polynomial. And therefore, we assume that we have m data points, x1, f1, x2, f2, all the way till xm, fm. This was the basis from which this expression was obtained. And we noted that in this approximation, we are going to incur an error of the order of h to the power of m. Now, here we have to modify this a little bit. The data set is going to start with x0, f0 and go till xn, fn. So we have to make some minor modifications to this, and that is what I'm trying to talk about here. So x0 is going to be the reference point, and it is not going to be x1 because our first data point is x is equal to x0. Not surprisingly, f of x1 should be replaced by f of x0, which is f0. Other things remain the same. We are going to say that f of x is going to be approximated by a polynomial of order m minus 1 with the first data point given at x is equal to x0 by this expression that you see there. So here we are saying that the unknown function f of x, we are going to approximate it by a polynomial of order m minus 1 based on m data points. But the reference point is x0. So this expression should make sense to us. Now, what's in a symbol after all? Whatever you see as m minus 1, I'm going to call it as n. So n is nothing but m minus 1. Therefore, we can write f of x as Pn of x0 plus alpha h, plus the error should be of the order of h to the power of n plus 1. Because if m minus 1 is n, m should be replaced by n plus 1. What we are going to do going forward is, we are going to approximate the unknown function f of x by a polynomial of order n. So this polynomial will have n plus 1 coefficients, and therefore we have to work with n plus 1 data points, which we already have here. Remember, we are starting at I is equal to 0 and we are going till I is equal to n. That means we are having n plus 1 data points. So that works well for us. And the error is going to be of the order of h to the power of n plus 1. And furthermore, our starting reference point is x is equal to x0. Otherwise, everything is the same. So we can reach any x from our reference point by jumping alpha steps. So if you're given alpha, and if you know x0 and h, you can find out the value of x you're talking about. On the other hand, if you're given the x value, and you know the reference point x0 and you know the step size h, then you can find out the value of alpha. The other point I want to make is h, we can write it as b minus a divided by n. So the step size can be found out assuming that the points are equally spaced. We know the upper limit of x is equal to b. We know the lower limit of x is equal to a. So we know b and we know a, the domain over which you want to integrate the function. So if you had n plus 1 data points, you will have n intervals. For example, let's take n is equal to 3. How many data points are there? 4. x0, x1, x2 and x3. So there are 4 data points. So I'm assuming n is equal to 3. How many intervals are there? This is one interval from x0 to x1. This is another interval from x1 to x2. This is the third interval from x1 to x3. So there are 3 intervals. If you have n plus 1 data points for the entire curve that you see here, you will have n intervals. And the domain b to a is divided into n intervals, so that the width of each interval is denoted by the symbol h. That's called the step size. You take the overall width of the domain and split it into n equal subdomains. So h, all these h's are equal to b minus a divided by n, where n plus 1 is the number of data points. So that is this. H is equal to b minus a by n. And we can write alpha as x minus x naught by h. That's not surprising because x we defined it to be x naught plus alpha h. Therefore, alpha is going to be x minus x naught divided by h. So we are trying to find out this integral from a to b for the function f of x dx. And just as an illustration, we can break it into the integral of two subdomains. One subdomain goes from a to c. So c is somewhere in between a and b. The second subdomain integrates the function from c to b. So if you are having a function of this form, and let's say this is a, this is b, so the area under the curve can be obtained as the area under the curve from a to c plus the area under the curve from C to B. That's what this says. And we are free to choose this point C, right? I could have it here or I could have it here. So you will see I can specify where I should locate C, or I can optimize the location of C. This we will get to at a later point in time. But C you can pre-specify, or you can let the data and the function talk, and you can say what is the best point to have C at. In any case, we have said this one enough times. These definitions have also been spelled out. With all that background, I can write this. Note, I'm just integrating the function now from x0 to x1. That means I'm considering the first two data points, x0 f0 and x1 f1. So when you have two data points, you can fit a line. So I can fit p1. So n is equal to 1. Other things are the same. Instead of f of x, I'm going to represent f of x as p1 plus r1, the residual 1. So instead of integrating f of x, I'm going to integrate p1 and r1. And that is what this one shows. So integral of p1. Now we had dx, right? But we have learned earlier that dx is equal to h d alpha. Because if x is equal to x0 plus alpha h, given that h is a constant and x0 is a constant, I can write dx is equal to h d alpha. So wherever you see dx, I can replace it by h d alpha because the polynomial p1 is going to be in terms of alpha. So the variable changes from x to alpha, as we have seen it a few times earlier. Now, the limits of the integral also change because when x is equal to x0, alpha will be equal to 0. Please note that when x is equal to x0, x0 plus alpha h on the right hand side. So x0 comes to this side, you have 0 is equal to alpha h, and we know h is not 0, therefore alpha is equal to 0. So x0 in the new variable alpha changes to 0. And x1 changes to alpha is equal to 1 because x1 is equal to x0 plus alpha h, and therefore x1 minus x0 is equal to alpha h. And using the definition of h, we know x1 minus x0 by h is going to be equal to alpha in this expression, and x1 minus x0 by h is nothing but equal to 1. Therefore, alpha equals 1. So this is the upper limit of the integration. So x1 in the new variable alpha becomes 1 and x0 becomes 0. So we have successfully integrated the first part. All right. If you go to the second part, the residual r1 is going to be of the order of h squared. Remember this expression. The error is going to be of the order of h to the power of n plus 1. Here n is equal to 1. Therefore, the residual term is going to be of the order of h squared. And again, dx is h d alpha, and the limits for alpha is 0 to 1. So this is how you are getting a representation of f of x, acknowledging this is the approximation and this is the error. So when you add 2, you are going to get exactly f of x. Now, if you just estimate this, you're going to get an approximate value of integral f of x dx. So what we do is integral x0 to x1 f of x dx is given to be integral 0 to 1. So what is p1? We have said that p1 is 1 plus alpha delta times f0. Let's see whether this is p1. Let's go back here. I'm going to replace m minus 1 by n. That is what we already said. When we use n is equal to m minus 1, pn of x0 plus alpha h is going to be 1 plus alpha delta plus alpha into alpha minus 1 by 2 factorial delta squared plus alpha into alpha minus 1 into alpha minus 2 by 3 factorial delta cube plus and so on plus alpha into alpha minus 1 into alpha minus 2 all the way till multiplication with alpha minus n plus 1 times delta to the power of n f x naught. So the expression written in green color is exactly this one with n equals m minus 1. So we have just changed the symbol, nothing else. So when n is equal to 1, p1 x naught plus alpha h is 1 plus alpha delta multiplied by fx naught. And fx naught is nothing but f naught. So that is why you see this expression here. Now, if you integrate this, right? So here I'm integrating it in the margin which I'm showing by my handwritten work. So the first term is going to be 1 multiplied by f naught h. So f naught h. The second term is going to be alpha delta multiplied by f naught h. So h alpha delta f naught. And these are easy to integrate with respect to alpha. The first term will integrate to f naught h alpha because f naught h is like a number, it's a constant. So integral of d alpha is alpha. So that is what you see here. Then delta f naught h, integrate alpha, you get alpha squared by 2. So this term also makes sense. It comes from here, integrating this term. And we have to set the limits from 0 to 1. When you put alpha is equal to 1, you get this to be f naught h and this to be delta f naught h 1 squared by 2, which is delta f naught h by 2. And when alpha is equal to 0, you get 0 from this term and 0 from this term. So the answer of the integration evaluated at the upper limit, which is alpha is equal to 1, minus the answer of the integral evaluated at the lower limit of the integral, which is 0, is the value of that definite integral. So you can see that is going to be equal to f naught h plus delta f naught h by 2. Now I'm going to pull h by 2 out. So when I do that, I get h by 2 in brackets. Because I pull h by 2 out, I can write f naught h as 2 f naught h by 2. So I pull h by 2 and h by 2 as a common term outside. So I get this. Then in the brackets, it's going to be 2 f naught from here plus delta f naught. And delta f naught is nothing but f1 minus f naught. Therefore, I get the whole integration of this term to be equal to h by 2 f naught plus f1. Let's focus on the other integral. So you have this to be of the order of h squared because n is equal to 1, order of h to the power of 1 plus 1. So order of h squared times h d alpha. So you have a term which is of the order of h squared here. This is exactly of the order of h. So you multiply the two, you're going to get something of the order of h cubed. An integral between 0 to 1 d alpha is going to be alpha. And between the limit 0 to 1, that integrates to 1. Therefore, this integral is going to be of the order of h cubed. That's what you see here. So the integral from x0 to x1 f of x dx can be written as h by 2 f0 plus f1 plus an error of the order of h cubed. So this is going to give us the approximate value of the integral because you have used linear approximation for the function. So this also is called the trapezoidal rule. So f0 plus f1 is the sum of the parallel sides like I talked about in the previous video. H is the width of the interval, the height of the trapezium if you like, right? When you look at it sideways, that's the height of the trapezium, the distance between the parallel sides. And you have half. So half into h into f0 plus f1 is the area of the trapezium. And you get the trapezium by assuming the connection between f0 data point and f1 data point is a linear connection. So first order interpolating polynomial. Now, if you want to evaluate the whole integral from a to b, you're going to set up these several trapeziums. In fact, you will have n trapeziums. And for each trapezium, you'll get an expression like this and you will add it up to get the overall. So the result is given here and we'll try to see how. This is a sketch of the function f of x. I'm showing 4 of the n plus 1 data points. So this trapezium is going to have an area half f0 plus f1 times h. This trapezium is going to have an area half f1 plus f2 times h. The third trapezium, if you can visualize that, is going to have an area of f2 plus f3h. And the last trapezium is going to have an area half Fn minus 1 plus Fn multiplied by h. So if you add up all this, you'll get the total area under the curve from x0 to xn. So if you take h by 2 as the common thing which occurs in each trapezium area, right? So this is the first trapezium, this is the second trapezium, this is the nth trapezium. So always you see h by 2 there, right? H into 1 by 2. So h by 2. Then I'm saying f0 plus h1 from the first trapezium, f1 plus f2 from the second trapezium, f2 plus f3 from the third trapezium, and so on until fn minus 1 plus fn from the last trapezium. So you will see this is the same as h by 2 f0 plus, you have two f1s there, so 2f1. Then you have 2f2 here, so plus 2f2. So you can do that, and if you can visualize it, till fn minus 1, you are going to have two terms, one from one trapezium, one from the other trapezium. As I said in video 1, the internal points, right, will feature in two trapeziums, one to the left and one to the right. So this 2 makes sense to us, why that happens. And the last will be just fn. The last data point and the first data point form only part of one trapezium. So this first data point will be only in the first trapezium. This last data point f1 will be only in the last trapezium. So this is what you get. This is exactly what you see here. Kindly expand this from I is equal to 1 to n and you will see what I mean. So between x0 and x1, the error is of the order of h cube. So this is called the local error because it is based on the subdomain x0 to x1. But when you want the error for the entire domain, you have to add this up n times, right? Because there are n trapeziums. So you're going to add this thing up n times. So that is what the summation I is equal to 1 to n means. So you're going to have n terms of the order of h cube. Now what is n? N is nothing but b minus a by h. So I can replace n by b minus a by h times something of the order of h cube. So you have b minus a divided by h multiplying something with the order of h cube. So this is going to be b minus a multiplied by something of the order of h squared. So when you add up all the local errors, the global error will be of the order of h squared, which is worse than the local error because the local error is of the order of h cube. And you can understand, globally the errors will all add up and then you will get a overall error of the order of h squared. And that's exactly what I've illustrated there, right? So I'm saying the integral from a to b is the same as the integral from x0 to xn, and I can break it into n different integrals. Each area I have indicated here for all the n trapeziums. Of course, I've displayed it for the first trapezium, second trapezium, and the last trapezium. And then I put it all together, right, to get this one. And I have written the expressions for you earlier. And I've also argued why the global error is of the order of h squared by doing exactly what we did previously. And the value of the integral is h by 2 multiplied by f0 plus 2f1 plus 2f2 plus all the way till plus 2fn minus 1 plus fn. So this is the trapezoid rule, and this is the formula for the area under the curve or the integral of f of x using trapezoid rule, which uses a linear interpolating polynomial over two successive data points. I'll stop here and I will catch up with you on another video. Thank you for your time.